I want to spend a little bit of time talking about how we manage data in the group, because I think this is also fairly important. All right? So, what I'm showing you here under the real Fremont is actually the data collection. Okay? So we collect data by plot number. So that plot is our experimental unit. Okay, and here we've got a harvest date in Julian days, right? So we can treat it as a number. I have a plot height and a plot width, so this is kind of vine size information. And then you see here total kilograms per plant, and I've cut it off, but it keeps going. Okay, we have a number of yield-related traits that we've collected data on. So the point that I'm making, though, is that when we're collecting data, we don't care about pedigree, we don't care about genotype. All we care about is this identifier of plot. Year and plot are unique in the history of the program. Okay, so if you give me the year and the plot, I can go to our seed vault and pull out one bag of seed and tell you what the pedigree is. Okay? We associate that with the genotype and then pedigree information. All right? Then we have this information on the column block, the row block, and the quadrant block. Okay? That right there is our augmented design. Okay? And you can see that we have checks that are replicated. Okay? So in our case, the check is a commercial hybrid, one that dominated the Midwest for years and dominated the northern Italian market for years. Okay, so it's among the best. It's not just anything, it's a good variety. All right? Okay, so these are the pieces of information that we have. All right? Worcester is on a different format. Okay? Worcester is on a different format because we only have a single row transplanter here, so we can't do 3 rows at a time. Our fields tend to be smaller, they're not on beds. It's a different environment. And then the data still have the same sort of structure, right, where we're connecting year, location, genotype, and then the augmented design factors back to the data that we collect. All right? But it's important to note that there is no connection experimental between column block in Worcester and column block in Fremont. No connection whatsoever. These design factors of column block, row block, and quadrant are only there to help us to make corrections for within environment. Okay, so we have to extract the BLUP for each trial separately and then combine our data. The first question that we're going to ask is very simple. Is there spatial variation in the field? Okay? And if the answer to that is yes, we're going to normalize to the nearest check, or we're going to estimate a best linear unbiased predictor. So how do we address this question, is there spatial variation in the field? You can run the LM function, right? Just do a fixed effects model, right? And the truth is, in the core package, there's also an AOV function for analysis of variance, which we haven't even talked about. But you have multiple ways. So we know how to do a statistical test to ask whether there's a row effect, a column effect, or a quadrant effect. Okay? All right. So it's time to crank up R, if you haven't already done so. We can go ahead and read in the data. So notice that what I'm doing is I'm having you read in 2 separate files. One actually has the phenotypic data, and the other is the field book that has the experimental design information. Okay? And you can go ahead and check those to ensure that the data are imported correctly. Look at the dimensions and look at the structure. And then you can merge that data. And so I'm introducing you to the merge command here. we're telling it to merge data that are in the files data F and data link, and we're telling it to use plot to do that. All right, so just to make sure that we understand is plot has to be the header in there, and there have to be plot numbers in common for this to work, right? So it's using this as a variable, so if I have plot all capitals in one file and plot capital P, small l, small o, small t in another, it's not going to be able to make that merger, okay? And again, you can check the dimensions of the new data, and then we can go ahead and attach it to make the rest of the coding easy. Okay, and I'm going to walk you through what you should be seeing when you look at dimensions F. So there are 324 observations for 14 variables. And then we look at the data. So plot is there, and these are all the traits that we've collected data on. So we have harvest date, maturity, right? Transplant to harvest is maturity. We have plot height, plot width, total kilograms per plant, fruit number per plant, ripe kilograms per plant, ripe fruit per plant, green kilograms per plant, green fruit per plant, culls, etc. Then we have 50 fruit weight and single fruit weight. Okay, so you could call these yield components. All right, but we're essentially looking at total yield, marketable yield, culls, traits that matter. Fruit number, fruit size. Okay. All right. If we look at that data link file, you see the experimental design variables that are relevant. You see the year, the location, the plot, which is allowing us to merge these two data sets, the pedigree information, and then these factors that we're going to use for our experimental design. And R is treating our factors as integers. Right? I mean, I could have called it A, B, and C, and then it would save me a coding step. And then I look at the dimensions, and you can see that we've now expanded that file, but it still has 324 observations. Okay? This is what we expect. So all we've done is merged two files. All right? So we're connecting our data to our experimental design. All right? And this is what the new data looks like. Okay? So plot occurs just once there. That's what we merged by. We have our experimental design factors down here, and some of them are being treated as integers, so we're going to have to tell R to do something about that. Minor problem. Okay. We can look at a distribution of the data. So if I want to change the y-axis so that it fits, I add this little y-lim equals C 0 to 80. So it's a 0 to 80 instead of 0 to 70. Right? And I just added that little line right up here. A couple of steps here. Let's go back. Okay. Notice, so this is in your script, but I didn't put it explicitly in a slide. All right? Notice the names here. Column block, row block, quadrant. Right? All right, so when I write out my model, notice my model. Okay, so I've had to tell R to treat column block as a factor and call it COL. Right, row block as a factor and call it row, quadrant as a factor and call it quad. Okay, I'm not showing you that explicitly because you can follow the script. Okay, but basically, I'm just putting these in as main effects, and I'm asking whether there's any variation explained by those main effects. And the answer is yes to all of them. Right? So I have variation in my field across columns, rows, and quadrants. So I should be thinking about correcting my data for those. All right? Okay. Another way to address the same question, is there within field variation, I can use the package LME4. All right. I can write out my model, my completely random model with genotype, column, row, and quadrant. Then I can write out a second model, in this case leaving out column. I can then do the comparison, ANOVA fit 1, comma fit 3. Based on a chi-square distribution, it's significant. And the model with column provides a better fit based on AIC, BIC, and the log likelihood. Okay? So it's just another way of addressing the question, is there variation across columns? Okay? I have to repeat this, leaving out row and leaving out quadrant.